Let's discuss sound interference in Quinck's tube. And this Quinck's tube is an experimental setup used to demonstrate sound interference and also to calculate sound speed in air. This is the typical setup of Quinck's tube, in which there is a fixed U tube which is having two openings at point P and Q, and there is a movable U tube which can slide over the fixed tube left and right. It can be pulled out, can be pushed in. In this situation, if a sound source or a tuning fork, say of frequency NF, is brought close to one of the opening at P, the waves which enters at P, these are divided in two parts. One is through the fixed tube A, it reaches point Q, and other through the movable tube B, it reaches point Q, and the two waves from the two paths will interfere in the detector which is placed over here. We can also place human ear over here to detect the perception of loudness at the opening Q, where the two waves coming from two different paths interfere each other. Now in this situation, as the tube A is fixed, we can say its total length or the length of this path from point P to Q will remain L1, and the other path which is of length say L2 from P to Q, this can be changed by sliding the tube B in outward direction. Now in this situation, initially B is adjusted in such a way that detector will detect a maxima. So we can write initially one detector records a maxima. This implies the path difference, which is L2 minus L1, must be equal to n lambda, because we know sound maximum is detected at the point of constructive interference, and one path difference in the interfering waves must be a multiple of lambda. Now we can say now tube B is pulled out to detect next maxima. That means if the tube is pulled out by a distance x, we can say if the tube is pulled out by a distance x, the total path L2 will increase by 2x, because if it is pulled out by x, x and x, total 2x length will be increased in the path of wave which is passing through the tube B. So for next maxima, if it is pulled out by a distance x, we can say the new path difference will be L2 plus 2x minus L1 should be equals to n plus 1 lambda, because for next constructive interference, the path difference must be the next integral multiple of wavelength. So from these two equations 1 and 2, you can see we subtract the 2, will get this 2x is equals to lambda, which is the experimental value of wavelength of waves which are propagating through the tube. So from here sound speed can be directly given as, here is sound speed can be written as frequency of tuning fork multiplied by the wavelength which we have detected, which is 2x. This is the way how we can find out the speed of sound in air by this experiment of Quinck's tube. And if the tube is gradually pulled out, we can easily detect alternative maxima and minima one after another, because the change in path difference changes the type of constructive and destructive interference, due to which loudness of sound varies in the detector. So at laboratory level, there is a very good experiment to demonstrate the phenomena of constructive and destructive interference by using the path difference. Even students can practically measure the wavelengths, and correspondingly they can match that the values which we are getting from here are in close approximation with the theoretical values we calculate on paper. So this is quite a good experiment for demonstration of interference in laboratory.